Good evening, everyone, and welcome to the 2022 Einstein Lecture. So it's great to have people here. The last couple of years, I looked in the audience, there's about 7 people here the last couple of years. But we did have quite a lot online, but we had about 7 people in the audience. So it's great to see a whole lot of faces around, and a lot of them even familiar. Tonight's event is presented by the New South Wales branch of the Australian Institute of Physics and supported by University of New South Wales Science and the School of Physics. I'm Honourable Associate Professor Graham Melville, and I'm a Fellow of the Australian Institute of Physics. I teach and do research here at UNSW Physics. I work on the atmospheres of exoplanets, and I also do nuclear physics, where I'm working with ANSTO to produce an Australian supply of actinium-225, which can be used in targeted alpha therapy for metastasis in cancer. So a couple of things there. I'm in the New South Wales committee, so I've got sort of like 3 hats, but I can't wear them all tonight. I would now like to acknowledge the Bidjigal and Gadigal people, who are the traditional custodians of the land that UNSW Sydney is built. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who may well be here tonight. The Einstein Lecture is an annual event presented by the New South Wales branch of the Australian Institute of Physics. We've had it here at the university for about the last 5 or 6 years. And it's, I would like to say right now, thanks to the Faculty of Science for helping run this year's event and covering catering costs. There was heaps of food outside there, and I thought it was pretty good. Lots of food and drinks and stuff. So that was fantastic, and I'm sure people enjoyed all that. Special thanks to Louise Barry, Sarah Remfray, and Fiona McLean from the Science faculty. This year will be the 17th Einstein Lecture, and past distinguished speakers have covered a wide range of topics with emphasis on Einstein's ideas and their consequences for physics and technology today. Topics have ranged from quantum computing to plasma physics and to astrophysics. The lecture engages audience with the wonders of physics, especially young people, and highlights the recent advances from world experts. And we certainly have world experts here tonight. The Australian Institute of Physics, or AIP, is Australia's premier physics organisation. It promotes the role of physics in research, education, industry, and the community. New South Wales branch is very active, and we have a number of activities such as lectures like this one. We have visits to places like ANSTO and CSIRO. We have student prizes and a whole lot of events. So if you look on our website, in fact later on this year, on the 3rd of November is the Physics Industry Day, 3rd of November at CSIRO at Linfield. And on the 8th of November is the Postgraduate Day. Now, travel agents would say it's always a good time to travel. Real estate agents say it's always a good time to buy and sell a house. In the AIP, we say it's always a good time to join the AIP. Now, about tonight's talks, gravitational waves and other things, you can't get any more Einsteinian than gravitational waves, which were a consequence of Einstein's general theory of relativity, although he doubted they would ever be detected. Why is that? Because of technology problems. Now, in Einstein's time, there were virtually no computers around. However, Einstein did know that there were 2 types of people in the world: those who understand binary and those who don't. However, when Einstein examined quantum theory, he was quite upset. One of the reasons for that, because he found out that there are actually 3 types of people in the world. So tonight's lecture, if Einstein was here, he'd probably describe it as spooky understanding at a distance. Now, tonight's speakers, okay. Born and raised in Old South Wales with a passion for astrophysics, Grant Lewis spends his time unravelling the dark side of the universe, namely dark matter, and the fact that it dominates the cosmos. As a professor of astrophysics at the Sydney Institute of Astronomy, his research focuses on cosmology, gravitational lensing, and galactic cannibalism. That sounds very scary, doesn't it? I hope there's no one in the audience under 12 years of age that might be given nightmares. Galactic cannibalism, wow. As well as exploring why the universe appears to be just right for life and complexity. He has published more than 400 research articles, and he also undertakes a broad array of award-winning science outreach, bringing the wonders of the cosmos to the broad audiences through public speaking and writing, including publishing several world-renowned books in the mysteries of the cosmos. Our second speaker, Tara Murphy, is a professor of astrophysics at the University of Sydney and a member of the Ausgrav Centre for Excellence for Gravitational Wave Discovery. She is a world expert on radio transients. These are astronomical objects that change rapidly with time. Since 2015, she has led the Australian effort in radio follow-up of gravitational wave events, culminating in the first detection of radio emission from a binary neutron star merger. And listen to this, GW170817. You have to remember that in case you need it later on. So she did that in collaboration with international colleagues. She has published 150 scientific publications on topics ranging from gamma ray bursts to flaring stars to pulsars. Tara loves sharing her passion for astronomy and has been featured on national TV and radio, newspapers, social media. Her writing has featured in the Sydney Morning Herald, The Conversation, Cosmos magazine. She has spoken at public events including Vivid, Sydney, the Sydney Astrofest and the Sydney Science Forum. Tara, I think you can probably add the Einstein Lecture to that one now. Okay, so tonight, as you can see, is Ripples in Space and Time, how gravitational waves have shaken our universe. Right, I will, first speaker, Professor Grant Lewis. We welcome him.
Okay, I'm Welsh, I can talk loudly. Okay, so thank you very much, and thank you for the invitation to give the Einstein Lecture 2022. So tonight's topic is gravitational waves, the last great prediction from Einstein's general theory of relativity. What we want to do tonight is basically tell you essentially what gravitational waves are, a little bit of history about how we come to understand gravitational waves, and note that we've been able to detect gravitational waves directly here on Earth for the last 5 or so years. And what we're finding is that they're already starting to reveal many mysteries of the universe. So the way we're going to do it tonight is that I'm going to give you a little bit of history, a little bit of background to the physics of gravitational waves. Tara's going to bring you up to speed with what's happening in the entire field of gravitational waves at the moment and what we are seeing. And we'll also let you know a little bit about where we think this topic is going to go. But our story starts tonight in a simpler time. We're going to start in the 17th century. Now, it was a simpler time, but they too had plagues and war and civil unrest. But for science, this was a very important epoch. For science, this was the time where modern science emerged. So we had the giants of science, namely Galileo and Isaac Newton, lay out the framework for what would become our modern view of the universe. Importantly, what they did is they showed that we could talk about the laws of the universe in the language of mathematics. So if I wanted to understand how this object interacts with that object, what I need to do is work out the equations that govern that interaction. And Newton quite famously gave us his law of gravity that tells us how one planet attracts another planet. Now, importantly for Newton, these laws of physics played out on a stage. And that stage is the 3 dimensions of space that we have around us. So we've got up, down, left, right, forwards, backwards. And so physics plays out on that universal stage. But for physics to work, we needed one more thing. And we also needed a clock. We needed the universe to have a time that ticked by regularly, and that clock applied all over the universe. So with this particular framework of the stage on which physics played out and the clock which ticks and physics abides, modern science developed. And it stayed that way for several hundred years. And what we had was this situation where all of our physical laws, we had more and more mathematics, etc., all of it was based on this same notion that that Newton put forward. All that changed at the start of the 1900s with Albert Einstein. Now, Einstein's problem was light. Light had been a mysterious thing since ancient times. The Greeks wondered how light worked, and all the way through the development of science, the question of what light is and how it behaved was central to many ideas. But it wasn't until the mid-1800s that the Scottish physicist James Clerk Maxwell showed us what light actually was. He discovered that light was a wave, and it was a wave of electricity and magnetism. And this electricity and magnetism basically fluctuates back and forth and propagates itself through space. Now, written in Maxwell's equations, right there in the center was an important number, and that was the speed of these waves of light. And that speed is quite fast. It's 300,000 kilometers per second. But what a lot of people noticed is that the equations didn't tell us what this speed was relative to. When you talk about the speed of an object, it's relative to something, right? So you have something here, something is moving relative to it, that's its speed. But nowhere in the equations did it tell us what this sort of reference was going to be. So some people suggested that the universe provided a reference, that the universe was filled with a material they called the ether, and light traveled in the ether. And that meant that if you were at rest with regards to the ether, you would see light traveling at 300,000 kilometers per second. But if you were moving, you'd have to add or subtract your speed from the speed of light. So everybody should basically measure the speed of light to be different. Now, Einstein didn't like that, right? He thought it was too messy. He thought it was too cumbersome. It made a mess of some simplicity that you want at the heart of physics. So he said, right, I'm going to do away with this concept that everybody measures the speed of light differently. And what I'm going to say is that everybody is going to measure the speed of light to be exactly the same. Everyone is going to measure 300,000 kilometers per second. Now, you can say that, but of course, what that means is you've got to get the mathematics to work to say that everybody measures the speed of light to be the same. And to do that, something else has to give. And when he looked at his equations, the only things that could be messed around with was Newton's idea of a stage of space and a universal clock that ticks time. And what Einstein basically did is said that we no longer should think of space and time as being two separate things, but they should be joined together in something that we now call space-time, and it's a bit more of an amorphous thing than Newton had an idea of. My concept of space and time and your concept of space and time might be different based upon how we're moving with respect to each other. So this was in 1905, and this gave birth to Einstein's special theory of relativity. And it was, a bit mysterious, this entire notion that we throw out the ideas of a great like Newton to replace them with these ideas that space and time is sort of more weird, okay, that you can mix them up. And there's a famous thing that was realized is that the passage of time, if you no longer have a universal clock that everybody ticks along to, clocks become a personal thing. Time is something that you experience, and the time that you experience and the time I experience might be different based upon how we travel. And there's a famous thing with regards to what's known as the twin paradox, that if you have two people on Earth, and one of them flies off into the universe at high speeds and flies back again, they will be younger than the person that they left behind. The person on Earth will age more than the person traveling on their journey. Now, it sounds weird, but it works. We can do experiments and show that this is precisely how time works. Right? Time is something that belongs to an individual particle. It's not a universal constant. So this made Einstein kind of famous amongst other physicists, but he realized that he had a problem straight away. And the problem was with gravity. And we all know what gravity is, right? Gravity is that force that holds us in bed in the morning, so you don't want to get up. Okay? It's a force that tries to pull us to the center of the Earth. And Einstein looked at his equations that he had developed for special relativity, and he said, right, I want to get gravity working in here, but it wouldn't work. Okay? Gravity in Newton's formalism depended on masses and distances, but Einstein had already said that all of this stuff gets messed up and it all depends upon the observer. So he decided that he would go back to the drawing board and he would basically throw out Newton's ideas of gravity. So he's already got rid of space and time. Now he's going to get rid of the notion of gravity. It took him 10 years, but he realized that he could get gravity to work if he did something strange with space and time. He discovered that gravity would emerge from his mathematics if he allowed space and time to warp and bend and stretch. Now again, it seems like a very strange thing to say, that space, here's a block of space, and that somehow there's bending and curving going on in this space, and that's what we experience as gravity. But it works. And in 1915, Einstein put forward his general theory of relativity, right? The theory that now included gravity. And it's a theory that basically says, I get rid of the notion of gravity as being a force. I'm going to represent gravity as being curving space-time. And in 1915, there wasn't really much evidence that this was actually the correct theory of gravity, but there was a crucial piece. And that was to do with the orbit of Mercury. So Mercury is the closest planet to the sun. It moves around the fastest. It's also in the strongest gravitational pull in the solar system. And astronomers had been charting its orbit. And it's a little planet. It orbits the sun, but it also gets pulled by the bigger planets. So its orbit goes around, and instead of just being a nice, simple orbit, it gets these little tugs in various directions. And astronomers could work out all those different tugs, but the answers didn't work. Right? They found that there appeared to be something happening to Mercury's orbit that couldn't be explained by just using Newton's gravity. But if you calculated the orbit of Mercury with Einstein's general theory of relativity, that extra little sort of shift in the orbit was perfectly accounted for. So that was good. And again, that made Einstein even more famous amongst the physicists. But still, most people didn't care, because 1915, that was when World War I was underway, and there were other things on other people's minds. But by the end of the war, people decided that they wanted to test Einstein's ideas. And 2 expeditions set out from Britain in 1919, one to South America, one to Africa. And what they wanted to do was observe the sun during an eclipse. So, of course, an eclipse is when the moon passes in front of the sun, blocks out the light, and you can see the stars behind the sun. What Einstein's equations predicted is that the gravity of the sun would act like a glass lens, and it would shift the images of the stars by a tiny, tiny bit. A very small amount, but a number that's big enough for astronomers to measure. And they returned in 1919, and they had confirmed what Einstein had predicted, and suddenly Einstein was not only famous amongst the physicists, he was famous amongst everybody. Okay? Written in the New York Times, lights all askew in the heavens. Okay? As you can see, a book for 12 wise men. That's how many people they thought understood relativity at the time. Okay? So, it works. And it's still the theory that we use to describe gravity today. Now, we all have a gravity general relativity device in your pocket. It's one of these. Okay? GPS relies on Einstein's general theory of relativity to work. Without it, the clocks would drift away and we wouldn't know where we were and we wouldn't get to the party on time. All right? Now, Einstein then wondered some more about this notion of space and time, right? If you can curve space and time, what happens if you pluck a little piece of space and time? Like if I plucked my skin when I was younger, of course, I plucked my skin and it would go back very quickly, nice and smooth. Is that what happens to space-time? Does it quickly just go back to what it was? Or with my now older skin, I pluck it and I let it go and it slowly returns to where it is? Or maybe I pluck it and the pluck just stays there. Or maybe I pluck a bit of space and time and it starts to oscillate up and down, like it's springy. And he wondered if space and time could be like water on a pond. Could I put a smack into a bit of space-time and cause space and time to ripple? And of course, you know, he has the mathematics of relativity in front of him. He goes down, he does all the calculations, and he finds that the mathematics says that if you put a wobble into space and time, that wobble generates ripples, and those ripples will travel. And so he predicted that if you have masses in the universe and they're orbiting each other, so they've got strong gravitational pulls and they orbit each other very quickly, that in those orbits, they basically set up these ripples in space and time which should travel from one place to another. Now, as Graham mentioned, right, this was predicted way back in the very early 1900s. And Einstein realized that these gravitational waves, as they're called, would be very, very weak. Gravity is an exceedingly weak force, much weaker than electromagnetism or the other forces. So these gravitational waves are really tiny, tiny waves traveling across the universe. You have to create them in very violent events, things crashing together, but they are tiny, tiny waves. And not only that, but Einstein had a bit of a crisis of confidence. And this happened more than once in Einstein's career. If you are interested, you should read the history of Albert Einstein, is that he flip-flopped on several of his ideas more than once. And famously, in 1936, he wrote a paper, Do Gravitational Waves Exist? And there's a famous maxim in science that if somebody asks a question in the title of a paper, the answer is no, right? And he did what he did with all of his papers. He submitted his paper to a journal for publication. And the journal did something that had never happened to any of Einstein's papers before. They sought a second opinion. They sent his paper to a referee. Now, to a modern scientist, of course, this is what happens to all your papers. It's part of peer review. It goes off to a referee. They write back comments about how you should write a paper more like the referee would have written it. And your science supposedly improves through the result. Einstein, however, was absolutely furious. Right? This is Einstein being furious. Right? He wrote back that he didn't send the paper to the journal for somebody else to read. He sent the paper to the journal for the journal to publish it without question. And he said, I'm never going to publish in your journal again. And he didn't. But in the time that it took between submitting the paper and going to the referee, etc., Einstein realized that he had made a mistake in his mathematics, and so he eventually published a paper on the fact that gravitational waves exist. Okay? But he still flip-flopped now and again. So he didn't like the entire peer review process. Again, Einstein died in 1955. The hope of detecting gravitational waves was well beyond any technology at the time, but people still wondered if it was possible. And people still wondered if they were real waves or were they mathematical waves that had no physical effect. The mathematics of relativity is kind of complex, so trying to make that judgment is hard. But in the 1960s, people realized that gravitational waves should do something kind of important. It's called the sticky bead argument, and it's essentially was put forward by Richard Feynman and Hermann Bondi, two of the big scientists from the last century. And they pointed out that if you have a wooden rod and you have a pair of beads on there, and a gravitational wave comes through, that gravitational wave is going to take those beads and it's going to pull them apart and push them together, pull them apart and push them together, okay? And as those beads move, that's going to have friction with the rod, and that's going to cause the rod to warm up. And the question is, well, where did the energy come from, right? If you warm up the rod, energy came from somewhere, and the only place it could have come from is the gravitational wave itself. So they realized that through this sort of argument that these waves should carry energy, which means that we should have a chance of detecting them. If we could build a wooden rod and a pair of beads sensitive enough to measure the tiny disturbances that we get with gravitational waves. Things changed again in the 70s. And it was these two guys, Hulse and Taylor. And Hulse and Taylor were looking at these very condensed stars known as neutron stars that are orbiting each other very, very closely. So this is precisely the kind of scenario that Einstein wondered about. If I've got two masses moving around each other, close together like this, should they be generating gravitational waves? Now, these particular neutron stars, they pulse, unimaginatively named pulsars. They pulse at regular intervals, and so they carry a little clock with themselves. So what you get is that as these two orbit, they're sending out this little clock signal, but we expect them to be generating gravitational waves, which is carrying away some of their energy, and that energy means that the orbits of these stars should be shrinking and they should be getting closer and closer together. And over the intervening decades, people have been able to use that clock to measure how they're orbiting one another and finding that the orbits are getting smaller and smaller as energy is being carried away by gravitational waves out into the universe. And the blue dots are the data, and the curve is the prediction from Einstein's equations, and the curve goes right through the data. So we know for certain that gravitational waves exist. Something is carrying energy away in these systems. But what we really want is not to infer the existence of gravitational waves. We want to detect gravitational waves. We want to build detectors here on Earth that will allow us to actually measure them and start to use them as a telescope. So we know they exist. We know they're weak. We know that we can calculate how these waves travel. Now, I know this looks somewhat biological, right? But this is a pattern of how a gravitational wave would actually travel. It's a bit more complicated than a wave on some water, but when it arrives, it has a particular property, stretches one way, then stretches the other, and stretches the other. And the big problem is that we know that they carry very little energy, and try as we might, building devices sensitive enough to detect gravitational waves just hasn't worked for decades and decades. So what I'm going to do now is pass various mics over to Tara, and she's going to tell us where we went from there.
Okay, can everyone hear me? Yeah, okay, so to keep going with this story, we're at the point where there's good evidence that gravitational waves exist. They've been detected indirectly through the Hulse-Taylor binary pulsar, but what people are really chasing is that direct detection of gravitational waves and their effect on Earth. So how do people go about it? Now, for those of you that have actually done physics or engineering at university, you might remember the Michelson interferometer from your undergraduate labs. The idea of how we detect gravitational waves is actually quite simple, conceptually, but building the instrument called LIGO to do it turned out to be a 40-year engineering challenge. So the way that LIGO works is that you have two lasers and you're firing them down these perpendicular arms. If that laser light it travels to the end of those arms, it hits a mirror and it reflects back to the origin. Now, if it's traveled the same distance, then those light signals, those laser signals, are what's called in phase, and you don't get an interference pattern back at your base. But if something has happened to change the length of those arms, and of course with the gravitational wave, what it's doing here on Earth is ever so slightly stretching and squeezing space-time. And so the length of those arms is a little bit different if a gravitational wave is passing through. So when that light returns to the base, it's now slightly out of phase, and it causes an interference pattern. By measuring that pattern and by measuring the exact properties of that signal, the idea was you could detect gravitational waves. Now, this instrument, LIGO, is 2 telescopes that are located in the US, the 2 original ones, and their arms are 4 kilometers long. Now, they use a really clever trick to get that light to bounce back and forward 300 times on each arm. So effectively, the interferometer is actually 1,200 kilometers long, which is what you need to measure a really, really weak signal. This interferometer can detect ripples that are 1/10,000th the width of a proton. It's almost unbelievable. I mean, even as a physicist, I don't really believe it, that we could detect a signal so weak. And you think about that this has traveled many years to reach us. So this project went on for about 40 years of development. And then finally, in 2015, in fact, on the 14th of September 2015, the first direct detection of gravitational waves was made. And this was of a binary black hole system. 2 black holes, one of them 36 times the mass of the Sun, and the other one 29 times the mass of the Sun. Astronomers gave this, or physicists gave this the name GW 150914, and Graham already joked a bit about the names. Astronomers are very famous for having really creative names for our objects. What does this name mean? This means that this was detected in 2015, September, the 14th of September, which of course is today. So yeah, today is exactly 7 years from the first direct detection of gravitational waves ever. So this led to the Nobel Prize in Physics, another Nobel Prize that black holes and pulsars and neutron stars and gravity was involved in. And it also opened up a new dawn in astronomy. So as Geraint mentioned, I'm an observational astronomer, and I'm going to talk about what we've learned about the universe because of this detection of gravitational waves. So one of the things that was really surprising about this detection was that it happened in the LIGO engineering run. They were just preparing LIGO to do the main observing run, and this signal came through. And this signal was way stronger than anyone had expected from our understanding of black holes and black hole mergers from the astronomy we'd done so far. So this plot is jumping forward to all of the black hole mergers and neutron star mergers that we know today that have been detected from LIGO. And what it shows, in the purple dots, they are the black hole systems that we knew about from astronomy detections previous to LIGO. So how do we know about them? That's because the black hole was orbiting with another star, and it was eating some of the material from the star, and so we could detect the signal from that with normal telescopes. Those first LIGO black hole detections, so these show the blue circles are what shows the binary black holes, and then each pair joins up to a circle above it, which is the black hole that it forms. And so you can now see that we've detected, as of 2021, a whole host of binary black holes, many of them far heavier, far more massive than all of the black holes systems that we knew about previously. And what we've also detected is a bunch of neutron star mergers, and that is what I'm going to talk about in a minute. Because so far, the result that won the Nobel Prize, it was so important for physics. It was the first direct detection of these gravitational waves. But it was almost unconnected from the rest of astronomy, because black holes, as you know, they don't have any stuff on them. They don't have any material on them. Nothing can escape from a black hole. So when 2 black holes merge, you don't actually expect to get any electromagnetic radiation. Now, the astronomy community around the world, we all pointed our telescopes at this black hole merger, but we didn't detect anything, and that was actually what was predicted. So we still had a lot of unanswered questions about astronomy and about physics, even after the detection of these black hole binaries. So we jump forward a little bit to the next LIGO observing run in 2017. And this is where we heard this famous chirp that started this new era in astronomy. So I'll just play it now. And then 1.7 seconds later, this ping. Okay, so what you're hearing there is this is actually the gravitational wave signal. Now, it's been converted to sound so that we can hear it. It's not really a sound signal, but it's the gravitational wave signal of the last few thousand inspirals of two neutron stars as they collide. So we've moved from black hole binaries, which LIGO was very good at detecting, but now we're detecting something else. We're detecting two neutron stars, or two pulsars, which is the second most dense thing in the universe. So the most dense thing that we know about is black holes. The next most dense thing we know about is neutron stars, which are basically dead stars, the remnants left over after a star has died. Until 2017, this signal had never been detected before in human history. We'd never seen something like this. But what was special about it is that at the same time that this gravitational signal arrived, in fact, just 1.7 seconds later, the Fermi telescope, which is a space telescope, a gamma ray telescope, detected this, a gamma ray burst, at the same time as this gravitational wave signal. And so for the first time, we had electromagnetic radiation and gravitational waves in the same event, and that turned out to be very important. The first reason it turns out to be important is that LIGO is very sensitive at detecting gravitational waves, but it's very poor at localizing them. In other words, it's like saying we detected a signal, but somewhere over there. We don't know where it came from. There's no way with the LIGO interferometer of localizing the exact position of that on the sky. And so we don't know from what object it's come. Now we have an electromagnetic signal. We were able to narrow that down, and astronomers started searching for the possible host of this gravitational wave signal. And so in Australia, I was leading the radio follow-up team. Around the world, there were hundreds of astronomers. We're all pointing our telescopes at this same location and started to search the galaxies in that to see if something had appeared in the same location as the gravitational wave signal. Now, finally, after about 9 hours of searching, a team of optical astronomers detected a bright flash in a nearby galaxy. That galaxy was called NGC 4993, and it's 130 million light years away from Earth. So what I'm showing here is the Hubble Space Telescope image of that galaxy, and then in the little box is this new object appearing. Now, one of the interesting things about this galaxy is that it was completely boring. This was just a completely normal galaxy. There was nothing that set it apart from many other thousands of galaxies around us. Now, what did these observations actually tell us about the merger and about the source of the gravitational waves? So before I explain that, I'm just going to do a little bit of a recap for those of you that might have forgotten about the electromagnetic spectrum. So I use normal telescopes that observe normal light. That light covers a wide range of frequencies, from radio light, which is what I study, very long wavelengths, low energy light, right up through to X-rays and gamma rays, which is very short wavelengths, very high energy light. Now, on that whole spectrum, Earth's atmosphere only lets in visible, optical, and radio light, and all the rest are blocked out. So to see those other wavelengths, we have to use space telescopes, which is what Fermi is. And so astronomers across the world were using telescopes at all of these different frequencies to try and study this object. I don't have time to go into what they all showed, so I'm just going to tell a very brief story of what each bit of this discovery showed. So we started with the detection of gravitational waves, and that was the famous chirp that I showed you before. And then 1.7 seconds later, the Fermi Gamma Ray Telescope detected a signal as well. And that showed that this merger had produced a very strong beam of radiation, really narrowly beamed and pointing towards Earth, which was great. That means we could detect it. If it was pointing somewhere else, we wouldn't have been able to detect it. Now, about 10 hours later, an optical telescope detected a bright flash, which is called a kilonova. And when you see optical and infrared light, what that's telling you is something very hot is happening in the universe. And in this case, what it is all of the material in this merger from the two neutron stars coming together in a really dense, really hot environment and actually undergoing a process called R-process nuclear synthesis and producing heavy elements. So you have this massive explosion and all of these heavy elements being produced and all this matter being expelled. Now, many days later, X-ray emission was detected, and then 2 weeks later, we finally made a detection of radio emission. And what the X-ray and radio emission is telling you is a completely different part of the story. That's telling you about the shock front that's traveling out from that merger, from that explosion, accelerating electrons and sending X-ray and radio emission to Earth. So all of these different astronomers around the world, using all different kinds of telescopes, put all of this information together to make one big picture about what was going on. Now, I can't resist, because it's my area, showing you a very little bit of radio data, because you don't often get to see data from a radio telescope. Now, what you see this is real data here on the left. These are our observations of GW 170817. And what you see in the middle, when you see radio emission, what you're seeing is you're not seeing the stars in the galaxy. This is actually the same galaxy I showed you before from the Hubble Space Telescope, NGC 4993. But you're not seeing the stars. You're seeing the emission from the supermassive black hole at the center of the galaxy. And then up to the top left, you're seeing the shock from the neutron star merger appear. And we did these observations with the Australia Telescope Compact Array here, which is out in western New South Wales in Narrabri, and the VLA, which is in New Mexico in America. So this was our little contribution to the big picture. Now, what happens when you put all of those observations that I've talked about together? What happens when two neutron stars collide? They produce gravitational waves, but they also produce an enormous explosion, and I'll show you this artist's impression of all the different stages of that explosion over 2 weeks. So just getting the play button back, which has just disappeared on me. There, okay. So this is when you're seeing the chirp as they merge. And then you're seeing the shock. You're seeing material being expelled into the surrounding medium. And so you're seeing every stage of this explosion. So this is a complex thing. It's not just the original merger takes less than a second, but then you're seeing this complex explosion as heavy elements are produced, a shock front travels out into the interstellar medium, and all of these create different types of electromagnetic radiation that we can view on Earth. So what do we learn from all of this? We've got this enormous effort. We've got 40 years of engineering to produce this incredible LIGO detector that can detect gravitational wave signals that are so weak that they're only stretching and squeezing space-time by a fraction of the width of a proton. We've got 100 telescopes around the world looking at every frequency to see the effects of the explosion of this merger. What do we learn from all of this? So I'm just going to talk about 2 of the things that we learned. There are so many things, and in fact, on the day that this result from GW 170817 was released, there were 85 papers published on the same day just about this one object, which is incredible in science to have so much work done in such a short period of time and then published all on the same day. So the first thing is that this event confirmed one of the final predictions of general relativity. And of course, in the media, this was sort of, we proved Einstein right, again. because, as Geraint said, over the last 100 years, many aspects of the theory have been proved correct. So in this case, and I should say really demonstrated rather than proved, because we can't really prove anything in science, but we can observe it and confirm it. So in this case, there was a delay, you saw when I played the chirp, of 1.7 seconds between the detection of gravitational waves and the detection of gamma rays with the Fermi telescope. Now you think, okay, that's not exactly the same. You said they arrived at the same time, but there's a 1.7 second delay. But you have to think that these signals have traveled on a journey of 130 million years from that galaxy NGC 4993 to reach Earth. So if you consider a difference of 1.7 seconds divided by 130 million years, then it means that gravitational waves travel at the speed of light to a factor of 1 in 10 to the minus 15, which is pretty close to correct. So that's one of the really important results that comes from the GW170817 detection. A lot of people ask, okay, but why 1 in 10 to the minus 15? Why aren't they exactly the same? We don't believe that's to do with the difference in speed. We think that is to do with the physics of how those signals get out of the merger in the first place. It's not instantaneous for the gamma ray radiation to leave the merger. It doesn't happen instantaneously. Now, just to make one really important point that I forgot before, why do you need electromagnetic radiation to measure the speed of gravitational waves, to confirm whether they travel at the speed of light? Well, the problem is, with the LIGO black hole detections, we know where those events were in distance, but we don't know when the signal left. So we can't measure how long it takes to get here. With electromagnetic radiation, we know that light travels at the speed of light. And so from our neutron star merger, we know that we actually have a signal that we can use as a measuring ruler to work out how long it took the gravitational waves to get here, assuming they left at the same time. So that's the first big result. The second big result is this provided one of the explanations for how gold and other heavy elements form. So many of you will have heard the expression that we're all made of stardust, because you know that the only elements that can, all elements except for hydrogen, helium, and lithium, which come, some of them are primordial, they come from the Big Bang, all other elements up to iron are fused in stars. But once you get heavier than iron, it's not possible for it to be fused in a star. So where do they come from? Many of you will know that they come from supernova explosions. The death of a massive star at the end of its life provides the necessary density and heat conditions to have nucleosynthesis occur and to fuse heavier elements. But when we look at the amount of gold and platinum and so on in the galaxy around us, the amount that we see, it can't be explained by supernova alone. As it turns out, we measured that gold and platinum were generated by the neutron star merger, and so this is another way that they can be produced in our own galaxy. Now, the GW170817 merger produced between 10 and 100 Earth masses of gold. And so this really caught the attention of the media, because at the time, gold was $55,000 a kilo, which means it was about $100 octillion worth of gold. And that even got us onto the business news. So that was pretty exciting. So that was another big result from this merger, was that it showed how gold and other heavy elements form in our galaxy. So where do we go from here? We've got from only 7 years ago, the first gravitational waves were directly detected, and now we're already using them to learn important things about our own galaxy and the universe around us. The future of gravitational wave detection is now going in a multitude of directions. So firstly, and as Graham mentioned, I'm a member of the OzGrav Research Centre in Australia, where we're working on all of these things. The first thing that we're doing is improving our terrestrial interferometers. So we're improving LIGO. There are multiple nodes being added to LIGO in Japan, in India, hopefully in Australia in the future. And that will mean that we can detect more sensitive signals and we can localize the signal better to work out where it's coming from. So we'll be able to see more things like black hole mergers, neutron star and black hole mergers, and other things like that. But there's also another couple of things we're doing. Firstly, space-based interferometers. There's a space mission called LISA that will allow us to detect gravitational waves at different gravitational wave frequencies. So you might be thinking this is already a little bit like the electromagnetic spectrum. There's different frequencies of light, and now we're going to have different frequencies of gravitational waves. That will let us detect gravitational waves from different types of phenomena, including possibly primordial gravitational waves from the Big Bang itself. And the third area is something that we work on a lot in Australia, pulsar timing arrays. And this is one of the most incredible experiments you can do in space. Geraint mentioned that pulsars are extremely accurate clocks because they pulse extremely regularly. And you can time those pulsations to about, I think it's about 12 or 13 decimal places of precision. So imagine you've got hundreds of pulsars in our galaxy, and you know exactly how they're timed. You know exactly when their pulses come. And then imagine a massive gravitational wave rippling through our galaxy. All those pulsars have their times distorted by a tiny amount. And so you can actually use an array of pulsars as a massive telescope for detecting gravitational waves. So this is the future. This is a new window on the universe. This is a new area of astronomy and physics. So I just want to end. I'm going to play one of these cool simulations again as we end. And I was thinking as we were preparing to give this talk, think about this 100 years. From the start, where Geraint was talking about Einstein's development of general relativity, making those predictions that have slowly, over 100 years, been confirmed by different observations. And then you're thinking 40 years ago, people are starting to develop this interferometer. It's based on a really simple idea, but the level of engineering precision you need to be able to detect gravitational waves is incredible. We have the indirect detection of gravitational waves through the Hulse-Taylor binary. We have building LIGO. Then in 2015, almost exactly 100 years after Einstein proposed that theory, we make a direct detection of gravitational waves. Then, in the 7 short years, literally 7 years from that moment to today, we have taken gravitational waves from this detection, this Nobel Prize-winning detection of one object, to using them as tools to understand our own galaxy and our universe. So I think in conclusion, what an incredible set of predictions by Einstein, but what an incredible century of physics that has been. Thank you.